Hello, can you hear me clearly? Hi Amar, hi Bhupati, hi Srini, Sanjay, good morning. Hi Amar, can you hear me? Okay. Good morning everyone. How are you doing? Good, good, good. So great. So everybody is able to hear, and others are also joining in. Hi admin, could you? What's your name? I see that I mean your name is admin, but good. So I'm just waiting for others to join in. I'm good, Bhupati. How the things? So, so out of you who all have not attended the first class, or so all of you have attended the first session. Okay, okay. So Amar has not attended but has gone through the PPT and recording. Okay. So Amar, please put down your, if you have any doubts, any questions, could you just write that down? So that, could you just ask that questions? And Bhupati, are you? I mean, have you attended our first session? This is the second session of the course. First session is an introductory session, which is public and free. What about you, admin? What's your correct name? Could you just tell me the name? Okay. Okay. Hi, Vanaja. So, if you guys have any questions, just please ask the questions right now with respect to the first session, so that I'll be answering those questions. And I'm just wondering why you haven't. There are total number of 10 people in this session, and there are only 5 people I mean, logged in right now. I think we should start now. We are already 7 minutes past after 7. And so, do you guys have any questions with respect to the first session? No questions. Should we do a brief recap of the first session? Okay, okay. So, Sini Sanjay, I'll just go through. If you have logged in into our knowbigdata.com, and under the after you log in, you will see my courses over here. Under my courses, if you say click on 18th October one, here you will see that there are installation instructions, presentation, quiz, right? Under installation instruction, there are detailed instructions on how to connect to the name nodes, and we will discuss these again after some time, after the recap, how to use it, and I will give a demo. All right? Yeah. So, Sini's question is that how to start using your labs. Sin, you can ask I mean, you can ask your questions to all the audience so that I don't have to repeat the question, and it's completely all right. Good, good. So, great. Let's now start. So, in the first session, what we had discussed is what exactly is big data and what is Hadoop. All right. So, let me just go through slides really fast. And so what we discussed was that something about myself, and this is the course content. So what is big data? Big data is simply huge data that you can process with usual tools, and you require distributed architecture. and structured or unstructured. Just a second. Hello. Yes, yes. Hi Rajnikant, are you able to join in the session? Yes, yes, we are all in the middle of session. Okay, yeah. So please join in. Are you facing any problem? Okay, okay, then join in, please. Yeah, thank you. Hi, somebody is trying to join in, so he was facing some problem. And so big data is basically the data huge size which you can process with usual tools and distributed architecture needed. So here the most important point to be noted is the distributed architecture needed. So almost all the tools will have that property. Distributed architecture as in the same tool runs on hundreds of computers or more than one computer and they coordinate. So all of those tools work together to accomplish a task. And this is the standard one. This is okay. We all know how many bytes are in petabytes. Now, because of the internet, because of the connectivity improved and devices improved, the lot of data has been generated out of CPU, memory, and disk drives and network interface card. Out of all of these fours, all of these four components play an important role in processing, and either of them become, you know, insufficient when handling big data, and therefore multiple computers are required. And when you add multiple two computers, these all are doubled. All right. These are the few examples of big data customers, and during our session, we will be taking a recommendation engine as a case study in the last session, and one case study will be about what happens when you keep on increasing the load on a website. And these are the common myths. This is the about jobs. So this is about Hadoop. Hadoop was created by few people based on Google's papers for their search engine. And Hadoop basically consists of these components as a part of architecture. So we'll be talking mm, HDFS, all of these components will be covered, plus one more component called Zookeeper will be covered other than this, right? And so this was the challenge which we were trying to solve. All right. So yeah. So we were trying to solve a challenge where we had to store 100 terabyte of data and in this manner. Now we had 100 terabyte of data when we were trying to store it. And how did we do it was first using a folder structure, and we had 100 drives and we stored all of this data. Now, just a second, just a second. Rajnikant is not able to hear anything. That is why he's having a bit problem, because it's a first officially the first session for him. Therefore, it is a little difficult thing. Okay. Sorry for the disturbance, but okay. So the number is from for United States. Okay. Rajnikant, the number is only for US, as you can see here, and it will be a little costly for you. Okay. Try try checking your settings in playback devices. All right. So okay. So here, to handle that 100 terabyte of data, we how do we store it and where do we keep it? So the way HDFS is modeled, HDFS is the solution to handle petabytes of data at very ease. So HDFS is made up of two kinds of nodes, admin nodes and data nodes. Admin node is singular entity, while there are multiple data nodes using which the data can be managed. Right. So data nodes keep all the actual data, while admin node just keep a note of where is what data, just information on top of that. So whenever you are trying to store, you ask admin node, and admin node tells you that go to this data node and store your file. And each file is split it into chunk of 64 MB, and that information, which chunk is stored on which data node, is kept on the admin node. All right. And with respect to replica factor, each replica factor is, I mean, decides how many copies of the chunk is available in the network. Okay. So each chunk or block, we will be using the term chunk block interchangeably. We'll be using chunk and block interchangeably. All right. And so in the admin node, you keep all the metadata, and in that data nodes, actual data is stored. Each file is split into small chunks of size 64 MB or 124 MB, 128 MB, based on the configuration. So this is how the HDFS generally performs. This shows you that what happens inside. So what you do is basically the client which you're going to use goes to the name node and and asks way how to store your file. Okay. So and then name node, once the client who is going to store the data, or data is informed by the name node that you go to these data nodes and store your file from this bytes, this location to this location in a data node, and then you start storing your file into these data nodes. All right. All right. So that is about HDFS architecture. So name node stores all the metadata, while data nodes actually store all these small chunks of the file. So for the demonstration of the HDFS file, first of all, go through the Hadoop installation document, right? It is available on your course page here, session one, and there you can see the recorded session also over there, and the installation instructions, right? So to connect on Windows, you can use putty. Okay, you can use putty. With the link is provided over here, right? And then you can directly connect to the, or if you're on Unix or Mac, you can directly connect to our servers directly, like this. You can see on my screen, right? So I'm logged in now, and so here you can, this in this folder you it's do not put much of data because it's a local file system. It is not HDFS. Okay. If you are going to create the data over here or on any of the servers, just create your own folder under this. The way I have my folder as Giri. So okay, so in this I keep all of my data. Similarly, you should also keep. We have not created separate logins for all the users. These are the logins of other students. All right. So similarly, you can also create one of your folder and then start using it. Okay. So we have kept in a single login so that all of you can start using it. But do not disturb any others files. Okay. Do not disturb anybody else's files. And why I have kept it open, so that you can learn from each other and see what, if you have to coordinate and ask other people there, then you can quickly see their file and even the assignments. All right, so that way you will learn from each other. Now here, okay, so good. Now here I'll just go to my folder and I'll say Hadoop file system minus ls. Okay, so when I say Hadoop file system, it basically goes to the HDFS and is asking for a list of files, and this is the list of files. Okay, so this metadata is basically coming from your admin node. These are the four files folders created on HDFS. Again, it's a shared space, so be careful about what you do. And from the same thing, if you have to do from the web, you can do 8000. And so there are two things. One is we have Hue. Hue is the web application which helps you interact with these components. Okay, you can interact with basically Pig, Uzi, Ambari, HBase, Stop. You can interact with MapReduce and you can interact with HDFS. All right. So see, if you see in the file browser, this is the HDFS which is being shown over here. Okay. And if you see there are users, this is the view I'm seeing because I have logged in as administrator. So I can see everybody's files. Okay. All right. So let me just sign in as a student. So here is your folder. Create your own folder over here and then start working. Right. So you can create a folder here, say new file or directory. So you create your own directory and then you start using it. So this is your HDFS. This is how you interact with it from the browser. So these are all files from all the users. And say for in my folder there is something called ratings, which is 11 MB, and this file it would be stored in in a single node. So I could try storing a file of say 200 MB on the cluster. And when you try to upload a file of 200 MB, you can upload from here. Click on upload, and then you first go to your folder, whatever folder you created. Okay, say for me, like my Asgiri folder is there, and I can simply say upload my file. So I'm basically uh, taking a local file and uploading it to to the network, to the HDFS. Okay, I don't have a 60 more than, there is only one file which is slightly bigger than 60, but I don't have a file. Okay, okay, let me just see if, so it's now uploading that file. And in the meantime, this is Ambari. So this is using the Hue, which is basically a web-based interface to all of these components. You can interact with services like HDFS, which is this file structure. Then you can interact with Pig. Pig is here. You can write your query. Okay, here you can write your query, save it, and execute it. And there is Hive. You can write Hive query over here and run it. All right. Then you have Job Designer. Using Job Designer, you can create your full flow and start working on it. Then you have Uzi. You using Uzi, you can define your workflows and start experimenting with it. And yeah, so this is the way you interact with the cluster from the browser. Now, in the similar fashion, there is a web interface provided to you on which is called Ambari. Ambari is a very important tool. Ambari helps you control all the services. As you can see on the left hand side, it shows you HDFS. It shows you that the secondary name node is down right now. Okay. And if you are planning to set up a cluster, you should probably be using using Ambari for handling all of the load. Okay, load of installing these apps, moving apps from one node to another. So all of these components are installed as services on these nodes. Okay, so all of these, say HDFS, Yarn, MapReduce, all of they are running that way. But here, if you can see, the region server has gone down and HBase master is stopped. You can restart it. Okay, you can restart it. Okay. On each machine, there are multiple services running, and these are the services. Okay, services like background process which keeps on running and serving to the users. Now the HBase master is up. So this is the list of all the services running in the cluster, and on which node what is running. So there are only four nodes: Hadoop 1, Hadoop 2, Hadoop 3, Hadoop 4. Hadoop 1 is a higher memory system, like 4 GB. Why? Because we had to install a name node on it, because name node needs a lot of memory. Hadoop 2 is also in the similar fashion. We wanted to run couple of services. It's a 2 GB memory. And this one is 1 GB and this one is 1 GB, which are data nodes. Data nodes do not require too much of RAM. All right. And these are the disk. And on these machines, say for example, Hadoop 1, let's see what all components are there. These are the components. Okay. So Hadoop 1 has got HBase master, Hive Metastore, MySQL, name node is there from HBase. And then resource manager is equivalent to task tracker. And most of the main servers are on Hadoop 1. Okay. Similarly, you can check what is going on with Hadoop 2. Hadoop 2 has got some more, basically, node manager is there, which is equivalent to task tracker. All right. So these are the nodes, and on each of these nodes, there are a lot of services running. Okay. And this is a good way to visualize all the services. We have only talked about HDFS and job tracker, task tracker. So, but you will, as you explore, you will get to know all of these services, and in a single glance, you can see this. So, whenever in an organization you are going to manage a Hadoop cluster, you will require a central control to manage each of the services, right? So, if there is a new computer which has been added to your network, all you need to do is you go here and say add new host, and then you can add more computers to the Hadoop cluster. Okay, and put the targeted host and then say register and confirm. But before doing it, you will have to install Ambari. This is Ambari. Ambari does the all of the Ambari agent. You will have to install before adding a node onto the cluster. So you install Ambari node. We will give a complete demo of how to set up a cluster. All right. Similarly, if you want to move a particular service, yes, Ambari is completely open source. If you have to move a particular component from one node to another, say I have to take this, so service action is there. If I have to say move name node to another computer, okay. So name node was running on one particular machine. I can easily move it from one node to another in your network. Okay. The moment you realize one particular machine is giving trouble, you can start moving all of this using Ambari. Ambari helps you a lot in that. Make sense to you? Here also, if you say service actions and then say move, then you can move this service from one node to another. All right. So this is about Ambari. Ambari provides you all these nice interfaces for controlling the admin control of your network. It helps you install, but before installing, you will have to install Ambari server, this interface first on a machine, and then Ambari agent on all the nodes which you want to add to the cluster. And using Hue, we were trying to browse the file in the similar manner. And here, let's see what happened. So it uploaded my file, which is Adam Mac, but this is also below 64 MB, so it will be stored on a single node and can delete forever. So it's as simple as that from the browser, but from the command line, it is little more cumbersome. So you type a command called Hadoop FS. Hadoop is a command line utility for both file system as well as MapReduce. And here we say Hadoop FS, and then we have all sorts of commands over here. You see, these are the various commands: copy, checksum, count, create, and df, du, and all of these commands are available. All right. How the replicas divided, 64 or 128 MB? In our case, I think it is 64 MB. Let's just see. Okay, let's just have a look. So we have got HDFS under config, under config. These are the memories, and okay, Hadoop maximum Java heap size, and okay. So block replication is right now 2. We can say 1. We can say 2. And then block size, if you see, this is the block size, which is 128 MB by default, right? In bytes, it is this much, and which means these many KB and these many MB. So it is 128 by default. All right. Hope that makes it correct. So Makhan, you did not miss too much, but you did miss a bit. So we were talking about how do we access and control the cluster. So there is something called Ambari server and Ambari client. When you have to install a Hadoop or anything in the network, all you do is you install Ambari server on one machine and Ambari client on all the machines. Okay, this is the interface which will be provided by the Ambari server, from where you can control or install any services. So first you install, and okay, so let me just discard my changes for time being. Once you install that, you can say add new host and keep on adding more and more computers to the network. It's as simple as that. Okay. Once you have set up all your cluster by adding hosts, then you can go ahead and browse the file using something called Hue. Hue is installed by Ambari. As soon as you set up all of this, Hue is also installed by Ambari, and there you can see the file system. This is my file system, and this file system is distributed all across the network. Okay, this file system is distributed all across the network, and that complexity is absorbed. That complexity is absorbed by our HDFS. So these files are actually stored on multiple computers. Okay, as you can see here, there are four hosts. Each of host is having multiple components, and if you see the dashboard of Ambari, you can see that there is HDFS storage, which says that it has got uh, total storage of 100 something GB. Okay, and we have got four out of four data nodes, and this is the basically this is the main control to see what is going on with you. And all of this is provided by Ambari in a very seamless manner. Okay, so you install Ambari server on one node and then start installing Ambari client on all the nodes and start adding them. And how do you add them? Just go here in host and start adding them, add new host, and then it will start. Okay, so and then whole game of your name node and data node will start. Okay. Now, this is very beautiful interface and quite simple and easy to files are easy to upload. But sometimes it is not only the browser is not sufficient. There you what you do is you use you will have to log into our machine Hadoop 1 or Hadoop 2 or whatever, and then you say Hadoop fs minus ls. So basically you are doing an ls on a SDFS cluster. Okay. So, and if you want to, if you want to see what is there in Asgiri folder, so this is there. If you want to say see last 10 lines, so Hadoop fs minus tail is also provided by them. And let's say these are the movie ratings. Let me just see what is inside that file. Okay, so it is basically a directory. Uh, all right. So this is the content of my file. Now let me have a look at. All right, somebody has asked a question. Can I log into? Yes, yes, please go ahead. Yes. So the information on what are the login details is provided under installation instructions in the session 1 and here. Okay. Under my courses. So you are supposed to actually log in and try out everything. All right. And so similarly, if you have to upload the data, what you say is copy from local, and then you give a local file name. Say I want to upload my jk jk.r, right, and under the folder asgiri. Now it has uploaded silently into my folder, and let's see. So remember that this is basically copying from local machine means hadoop1.nobigdata.com into HDFS. Okay. So if you are using a command line, there are two ways to do it. First, you install a Hadoop client onto your desktop wherever you are, and then tell the Hadoop client that our servers are located over there on Hadoop 1. Or first copy using FTP or using SFTP, you copy the data from your local machine onto Hadoop 1, and from Hadoop 1 you can push the data onto HDFS. All right. So is it clear to all of you right now? Okay. Okay, moving ahead. So, so right now, what we were doing is, if you use the web interface, okay, web interface from your local file, its local file, which is your computer, can be directly uploaded to HDFS, right? As I demonstrated here, here you can say new and then file, or sorry, no, not new file. You can say upload files. Okay, and there it will be uploaded. So the way we had just done, let me refresh it. There should be some way to refresh it. So jk.tar is just now we uploaded, and we can delete it. All right. Now, in the similar fashion, we can upload it quickly and browse your local machine and upload a file. All right. This is far, far easier. This is far, far easier than any other mechanism. All right. So from web interface, you can simply upload a local file onto HDFS directly. From the command line, there are two ways. Okay. Two ways to upload. First one is upload the file to Hadoop 1 dot no big data, or any of these machines, Hadoop 1 to 4, any of these machines you do upload using FTP, I mean SFTP basically, or SFTP or SCP we call it. And then once you have uploaded onto local machine, then you can do a Hadoop FS copy from local your uploaded file to the HDFS folder, your HDFS folder. All right, sounds good to you, right? Second way is, if you have to really upload huge data from your local machine or from your office intranet to Hadoop, the best way is, in case you have to move a lot of data, and you have to do it quite often. So best way will be to install Hadoop client on the on your local machine. We'll give a demo of proper this one. And then once you have installed a Hadoop client onto your machine, configure it. Configure it by editing HDFS. What file is that? If you can see that there is a, so under HDFS you have, so this installation is quite simple. You just download atar and untar it, and you will have uh, uh, those information available, I mean those files available locally, that command line. Now what I was talking about is, right, so HDFS site, that is called HDFS site .xml. Under HDFS site, configure it, and then under HDFS site you can mention your, so this, once you have installed Hadoop locally, you can add it HDFS site In this, you can see that there are many configuration, and here you can define the DFS data node address, right? Or you can define the where is name node. All right. Okay. So you can define your data node IPC address. Similarly, you can define your name node's address. All right. Here I have defined that this is where my name node runs. So configure it by editing this file, this particular property in this file. Okay. Here, once you install Hadoop, you can basically this is what you have to mention. Okay, and that's all. So now when you upload, when you say Hadoop copy, so here there were two steps involved. First, you uploaded the file from your personal computer to the Hadoop one, which is a cluster node. From cluster node, you push the data into HDFS. Here, first you installed a Hadoop client, then configured it. Now your Hadoop is set up on non-cluster one, your local machine, which any action you take over there will basically contact the name node which is located on our servers, like here. So when you say Hadoop copy Hadoop minus fs and say copy from local, okay, it is going to copy it is going to copy your local files onto the cluster, right? Here, so is it clear or did I confuse you guys? Amar, Virdi? Okay. Okay, so yeah, Prasant's question is that can I repeat? So here, what I'm talking about is I've not actually done anything. I'm just telling the steps. So in case say you have got an organization and you have hundreds of terabytes of data, all right, and your cluster is located somewhere else. It's your data is not inside in on any of the computers, right? It's not there on any of the computers running the cluster. Now, first you will have to transfer, either you transfer your data from your computers to the cluster computers and then push this data from local file system to HDFS, right? Or instead of making it two-step process, two-step is first from outside network to the cluster and from cluster to the HDFS node. Instead of these two steps, what you do is you first install a Hadoop thin client which will directly siphon your data from outside network onto HDFS and make it single step process. Okay, so for that you install Hadoop client, and after you have installed Hadoop client, tell the Hadoop client to upload that this is where my name node is, right? And once you tell that this is where your name node is, it will query all the information from name node and gather all the details and upload directly onto the HDFS cluster from outside the network over SSG. Yes. So uh, with this question is MV and repo, as in you mean to say that you require MVN to install Hadoop? Actually, you can install using apt-get, brew, or maybe manually. It's not such a big deal to install it manually. All you need to do is copy the binary files from downloaded zip file, and copy the config file to the appropriate location, and that's it. It's Hadoop only. Okay. Now the question is, yeah. Okay, okay. That means not required to store in the cluster. Yes. So you do not need to, in this approach, which I'm the last one, which is what most of the people do when moving the data from in and out of the organization, because this data is huge. When you copy this data, there are two losses. First, you will consume twice as much if you follow this first approach where you are copying this, you are going to consume twice as much as storage as required, one on your local and other on the remote machine, and then third one on the HDFS, right? So effective is thrice. Hmm. Or a better way to do is, I forgot to mention this here, right? So here, copy from local, you can also do a move from local. That will be very efficient. Right? This step moves your local data onto HDFS. HDFS can be, the data can be located anywhere inside the data node, so you really don't know where is your data. So therefore, when you say copy from local or move from local, there could be a transport again involved. All right. And this approach, which I'm explaining in the second step, is good when you have to move a lots of data every day, right? So you install Hadoop client on the machine which contain the data. From those machines, you first, and on those machines, you edit, after installing Hadoop client, you edit SDFS site, which is located in etc Hadoop and conf. So, I mean, this might be little vary, but if you run a find command, you will find this file, and change this property. Change this property to point to the name node. Okay. Now rest of the things will be taken care by the Hadoop client. And once you are done with installing this, when you run this command, copy from local, or or, or you say move from local, or you say dist copy. Okay. There's something called dist copy also, and dist copy is actually a wonderful tool. So we have Hadoop help, Hadoop fs, right? So here, do you see that? So append to a file is there, change group chmod, just like local file system, you have all of these commands. And there is, where is our dist copy? Okay, dfds, get merge, move, rename. Okay, okay, okay. So here, yeah, there is the dist copy. So you can do Hadoop dist copy, and then dist copy is like very wonderful tool from Hadoop. So the command is like this. All right. So when you are copying the file from a remote system, and you have got a huge folder structure, dist copy will be your best tool, because it will basically distribute the file properly, as in there is a outside network computer and is trying to connect to the cluster. Instead of getting heavy, if it keeps on connecting all the time only to one node, name node, and then relying upon all of this, it will be really slow. Therefore this dist copy is basically meant for a remote copying where it will figure out how to distribute the load across all the data nodes while copying the data. Okay. So that is how you copy the data. Okay. Either of these three mechanisms. This is without using any of the data import tools. So is it clear, Prashant, now? Or did I further confuse you? Okay, great. So I was talking about HDFS architecture, and we gave an overview of how to interact with HDFS using a browser and also using the command line. Hadoop is the command line, and when you say Hadoop FS, you get all these options. This is how you, using these commands, you interact with HDFS. Right. Now let's move on. So this is the HDFS architecture. Good. So does anybody has a confusion about HDFS architecture? Prashant, I don't see Apurv and few more people. There are three people who are missing. And yeah. So is everybody clear about HDFS architecture? Makhan, Amar? Okay, okay. So Vidhi is able to do all the commands. Great, great. All right, great, great. So, okay, okay. So what I suggest all of you that as we discuss, you should keep connected onto SSH onto one of the nodes, either Hadoop 1, Hadoop 2, or any of these nodes, and create your separate folder inside HDFS as well as inside Hadoop 1. Right. So Amar's question is, what do we do using command line when we can do it through the browser, right? That's a very good point. But imagine that you have got 1,000 files and you want to upload each one of them separately, right? So if you use a browser, you will be using one by one, one by one. But if you do a Hadoop a command line, you can use the command line for loop and all of those things to do it quickly. Okay. Okay. So SSH command over here is, so here, okay, so here it is, right? Yeah, you can do that. All right. And the password, as you can see, yeah, all right. And this is the login and password. You can see that, all right. Now, this don't touch anybody else's files because this is a shared login. And for shared knowledge, I've kept a single login for all. When you start working on your independent projects, then you will be provided a separate logins, all right, for the group. But right now, it is good and fun to actually see the other people's script. But just don't touch anybody else's script because that will, force me to create separate logins for everybody. And in case you are, okay, I'll have to take a call whether to create accounts for everybody. So, what kind of command list are we talking, Amar? The command list on Hadoop, you say Hadoop and say -fs, and you get all the command line. Not -fs, simply fs. You get a huge list of commands. These are the commands. All right. And if you type any command, it'll tell you. Right. So try exploring. We talked about move from local. We talked about ls. We talked about make directory. and see a copy from local, copy to local if you want to download any file, and tail is what if you want to just see last few lines, and there is a head command also, but it's not mentioned here, but there is a head command also. Yeah. All right. Now moving on. So everybody is clear about the architecture of Hadoop HDFS, what goes inside. There are name node and data node, and data node stores blocks of your files in a distributed fashion. Name node just contains the metadata. This ensures that all of your resources, your disk is properly utilized, and and the load is transferred across the network. All right. Excellent. Excellent. Let's move on. Now, compute engine we talked about. So in the compute engine, similar to HDFS, we have job tracker and task tracker. The the terminology has been changed. Job tracker in case of Yarn is called resource manager, and task tracker is called uh, job manager. I'll show you that one. So we have Ambari. Okay, Yarn is there. So we have resource managers and node managers. Okay. So resource manager is equivalent to the job tracker, and node manager is equivalent to task tracker. All right. There's a minor change in the terminology. Okay, okay. So we have talked about these components. Here, whenever we ask a job tracker to do a job, it distributes the job across the tasks, multiple nodes. So, does anybody has a question regarding how does it function? In a very simple words, we ask the job tracker to do the job. It asks task trackers to, it delegates to task trackers. When task tracker finish their job, it gives back the response to the job tracker via a queue. And these task trackers are generally located near data node. So whenever you give a job to a job tracker, you tell that this is the file which I want to process, and this will send the work to the task trackers which are closer to the data node containing your file which you want to process. Okay. So you have got say big file, you want to process it. It will have hundreds of chunks, and each chunk is located near a task tracker, and job tracker will be sending the logic to those task trackers which are closer to your data. All right. Now the thing here to be noted is whenever we are asking a job tracker to do the work, we are also telling job tracker that this is the file which we want to process, right? Remember that part. All right, so this is the recap of the first session. We talked about SDFS architecture, we talked about job architecture. Now there is a minor difference, as I told you, that Hadoop one, in the MapReduce took care of both the jobs. There were HDFS. HDFS is as is. HDFS role is to store the data for you. All right. Now the MapReduce is broken into multiple portions. Effectively, MapReduce was broken into two portions. One portion was proper MapReduce paradigm, just the paradigm part, the coding part. The second portion, the second component was Yarn, which was extracted out of MapReduce. Yarn does the resource management, as in what data node is closer to which machine, which task tracker, and which one is dead, and then all of this resource management is done by Yarn. And MapReduce basically uses Yarn to execute its maps and reduces onto the cluster. Okay, so MapReduce was broken down into two portions. One became pure MapReduce paradigm, and the other became the resource management part. And this was a very, very big deal because in because this opened the door to various other components, s- so that the other component can also take the benefit of resource management without I mean, the other components can also take the benefit. The other components can also take the benefit of resource management without using the MapReduce paradigm. They can invent their own paradigm to execute the computational logic across the network, right? Because there are cases where you are not able to convert your logic into MapReduce, and hence there were other kinds of like graph algorithms, the graph database, the Apache Spark, which does a different kind of processing a little bit. So all of these components can use the resource management of Yarn and the way MapReduce was using. All right. So that was the biggest difference between Yarn, Hadoop 2, and Hadoop 1. Okay. But important part to note is that any code you wrote in MapReduce is nothing but you write two functions. One is map, other is reduce, and tell the system to execute them. Maps are executed near the files on the on the data nodes, and once that finishes, the summarization happen using reduce function. We'll go into the details, very detailed. Now, so basically, whatever MapReduce you had written for Hadoop 1 were also valid for Hadoop 2, because this is not changed. This remains as is. Okay. So that was a good thing which was done for end user. For end user who were working with MapReduce, the whole change did not matter at all. This whole change, although it was a huge change, because of this change, the companies like Hottenworks existed. The guy from Hottenworks, who the founder of Hottenworks himself, did this change, splitted the MapReduce into these two, and that made Hottenworks a company worth noticing. Now, what kind of other databases are possible? These are the few examples. We have MapReduce, which does the processing in batch. You have Taze, you have HBase, you have Graph. This Giraffe is the important component. So it opened the door for so many applications who do not have to struggle with the resource management and can invent their own paradigm to execute the logic in the cluster. All right. So task tracker became resource manager, and and sorry, job tracker became resource manager. Yeah, job tracker became resource manager, and each each task tracker became node manager. That is the important part you should remember. Yes. So most of these applications run on the top of Yarn, and they are not comparable in feature because, say for example, MapReduce takes from you two definition of function. One is map, other is reduce. While Giraffe gives you an API to manipulate the graph, right? So these are two very different paradigm from a developer's perspective. All right. So the way you interact, the way you code is completely different, and that is really interesting. On the similar note, product like Apache Spark, they have a drastic difference in the way you execute your code. In case of Apache Spark, you write down your script step by step and then hand it over to Spark. And then it will run the script in step by step and distribute it and then bring it together. We will go into the details of each one running. So we have seen the web interface. We have SSH to the cluster, did a make directory and copy, then did a MapReduce command. MapReduce command we want to show you. Okay, and we will show you the MapReduce command, and then we'll show you the pig. And as I have told you that name node, our name node is on Hadoop 1, and data nodes are on Hadoop 2, 3, and 4. Okay. Just don't get confused. This only means that there are three name data nodes: Hadoop 2, Hadoop 3, Hadoop 4. Dot no big data.com. All right. Now we have got Ambari, which is running on 8080. Ambari manages the Ambari Ambari manages the servers. Okay. While Hue is basically for interact with services. Okay, so for end user, Hue is far more important. For system admins, Ambari is far more important. All right. So here you configure services. Here you use the services. So who is not able to successfully log in onto the cluster? All right. Or to log in, you can do student and then yes. Okay. So that you don't have to input the login again and again. Are you there? So are you able to log in onto the Hadoop 1, Hadoop 2 or whatever? Okay. Just anything you do, you just put it in your own folder so that it doesn't get, other people do not by mistake delete. Okay, okay, that's all right. Right. So install Putty on your Windows machine and use Putty to SSH. Okay. Yeah, it's up to you, Virdi. It's up to you completely. You can use those two also. All right. Now we have got this. So I have shown you that this is how you can upload file. Like I have big.txt and I can upload it onto the server easily. And these are the quick examples of how the pig query looks like. And this is an example of how Hive looks like, but there is no need to execute it right now. I just wanted to demonstrate to you that this is how it looks like. And now to see an example of MapReduce running, right. So you are right, Virti, because the only case is when the Hadoop one is too much busy locally. If there are too many people logged in or some process is going on the local machine, then you can utilize the Hadoop 234. All right. So here, this is how you delete a directory, and you can execute a Hadoop example like this. Let's see if it runs. All right. So to execute any MapReduce, you write your stuff into a jar file, and I'm just trying to locate a file called this one. So Hadoop jar, and let's see what happens. So it is showing me that these are the available options for Hadoop examples. These are the examples available. So this is the example jar which comes with Hadoop itself. So here there is a word count. All right. Now, so let me have a look at what file. So this is the basic example which comes with this. Okay, so we have got an input folder here. So here there is this big text files. The this big .txt file. I want to churn this. I want to operate upon this file. All right, just do not worry right now in case you are not in the context. I'll just fix the context in a minute. All right. Now, let me see if it works. All right. So now it has started. Let me talk a little bit about what I'm doing. Okay. So when you run your MapReduce job onto the cluster, what you do is, this is one example of if you are a Java programmer, this is how you can run your MapReduce. Okay, so you coded your map function and you coded your reduce function, created a .jar file containing the compiled code, and then what you do is you go to Hadoop command. This is the same command which you used with fs. Now we are saying, instead of fs we are saying jar, and then we specify our location of our code, where did we write, where did we put our jar file. Then these are the arguments. These are the arguments which we are going to provide to our program, right? Here, this particular jar file expects three parameters. First one is the word count. Second one is the folder where we have uploaded our files. And third one is the folder where the results will be saved. So here, it will start working like this. It says the folder already exists. You can say output 4. So all we are doing is whatever code we wrote, we have saved it in .jar file, and then we are asking Hadoop to execute the jar file and providing all the arguments required by our jar file. Okay, in this case it requires three arguments. First one is the command name, the example functions which it has provided. Second one is the input folder, where have you kept your file, right? And third one is the output folder, right? And this is started working now. So it's working, and in the meantime it gives you the URLs of various services which you can monitor to see what's going on with your process. As we have mentioned multiple times, that Hadoop is basically a batch wise process. Therefore, for each of the to monitor each of the process, you can open these URLs, and it shows you that this job is finished. Okay, the job is succeeded, right? If this job is succeeded, it would have saved the data in this output folder which we provided, right? This one. All right, either you can see it from your command line Hadoop fs -ls, or you can see it from the browser. Okay, and what does this command do? This example code which is provided, all it does is takes this file and counts the words in it. Okay, it's as simple as that. So for MapReduce code almost works like a Java code. Why do I need big data here? Or why big data has MapReduce? So okay. So Rajnikant's question is simple. He says that when we are just executing Java code, then why do we need Hadoop or anything, right? That's your point. I'm passing the input, MapReduce does the sorting, and it gives back the output, right? The important part is the whole game of executing your task on multiple computers is being done by Hadoop for you. Okay. Is that your question? Or your question is why do we have this kind of paradigm where map and reduces are there? So when you say why do I, right. So Rajnikant's question is you can do it without Hadoop also, right? But the thing is, all this distribution amongst all the multiple nodes, if you start handling the problems, okay. So So your question, his question is that when you can do all of this without Hadoop also, how can, if you have to do it without Hadoop, then you will have to build your own services. You will have to build a command which distributes the load to all these computers and read from HDFS on top of it. You will end up building the same thing, right? No? Okay, so we'll tackle this question in few minutes, and then we'll discuss. We'll go into deep dive into, right. Now here in this output folder, it has saved the data, right? This is available in part my dash r dash 000, and then to see what is there inside it, you can quickly see cat and then to it. All right. Now you can put the wildcard characters also. It works. Right. So here it has does the counting. Now you can see that this is not very clean way of, and if you see the same way in the input folder, what the kind of input folder which we have provided is a big file of big file. You see, it is a big novel. It can, so that word count has happened using a network system. Okay, it's very easy to do a counting locally also, but how if it goes beyond a limit, it becomes a very difficult thing to process. Okay, we'll talk about it in detail, and this doubt will get cleared, trust me on this. And this doubt, why do we need Hadoop in first place, will get cleared. Okay, now, so this is the example which I wanted to show you. How do you run MapReduce in case of all right, so I'm just putting this content back into. All right, so I just gave you a very quick demo of what does it look like. Can I do this? Okay, good. All right, perfect. So we are through with the example which we have just run, and do not worry in case you did not understand it. All I showed you that this is how you could execute your Java program, right? Now let's start with our exercise of starting to think in terms of MapReduce. Okay. Java process runs under which process? Does it run under Hadoop? Just trying to understand. Okay. So basically Hadoop is a Java process. Okay. If you see JPS, okay, okay, JPS is not there. So if you say PS minus AUX, PS minus AUX, oh, grab Java. So you can see a lot of things over here running. You can see, don't worry in case you see too much of text. Okay, let's see the first command which is running over here. You can see this one. All right, and here this is B sub X server, which is Hive server. This is Ambari server. This is another Java process, and there is this name node PS. Okay, there's a Java class called name node. It is also running as a process. So all of these are a Java process. Okay, all of these are Java process. All right. Java process runs under which process? What does it contain under Hadoop? Just trying to. So Prashant, is that clear? Was my answer clear to you? Great. Now, so MapReduce logic are inside the Java. Yes, yes, yes. So MapReduce functions were written inside that. Okay. Now I will go. Yes, you're right, Rajnikant. That's a good point. Yeah. Now, okay, okay. Yes. So yes, Rajnikant, you are right. It is required when we process a lot of data. Okay. Now I will start with a very basic question to all of you. Okay. The important aspect over here, why we want to discuss it, we want to think in terms of map and reduce, and this is a difficult exercise to do. Okay. So before we take a break or do anything, I'll leave you with a question. If you have a huge plain text file, okay, say you have all of the books, not only a Lord of the Rings, but all of the books of the world, or say of size close to a terabyte. Okay, close to a terabyte. If you have all the plain text of the world with 1 terabyte of the content, how would you find the frequencies of the world? Or just for simplicity, just take uh, 1 GB size. Okay, just take maybe 10 GB size. Okay, let's say 10 GB. That will not scare you. 10 GB. Okay. Now you have got 10 GB of plain text file, and all you want to do is you want to compute the frequencies of word. What will you do? What is it that you're planning to do? Okay. How will you find the frequencies of the word in this file? Okay. So we take a 10 minutes break, and we come back at 8:30, 8:44. All right. Let's come back at 8:44, have your quick breakfast, and then we'll again start. All right. And just think about this problem. If you have, how do you find frequencies in a text? Sorry. Hi, Amar. You must have received an email with the login ID and password. Didn't you get the email? Is it? Oh, I need to check that. I remember sending an email to you for the account. Okay, but for time being, just note down the password. I had told you the password. I'll send you the again. Okay. I didn't know that you haven't received. Okay. I'll call you after the session and then we'll see. All right. This is strange because I remember sending the email. Okay. Now getting back to the problem. But right now you know the password, right? For the cluster. Login is student and password is here. I have already sent on this chat. Okay. I have already sent you on the chat. Yeah. So this is the password. Okay. I'll just send it on the chat. All right. So for time being, you can use the cluster using these login password, and your personal login password for accessing LMS will be shared with you quickly. All right. No worries. And good. Now we're all set. We're all set. Now let's see. You are not able to log in, Vanaja. Where are you not able to log in? Which one? There are two login IDs, right? One on the cluster, Hadoop one 8000, and Hadoop one, I mean normal one, nobigdata.com. Hugh. Okay. Hugh, what does it say? If you go into this one, Hadoop one, what does it say? No, the login is student. Login is student. Okay. And password is this. Password is just I have typed password. Okay. So password is this. Try with this one, Vanaja, and then it'll be all right. Good. All right. So now we are getting back to the question which we I posed to you. So you have got a huge collection of text, 10 GB, and you have to find the frequencies of the words. What will you do? So Prashant said that first sort and then count. Right? That's a good answer. But my question was, how do you sort 10 GB file? And before that, before sorting, you will have to break the line into words, right? And then sort. So how do you sort that? I wanted to understand that part. Makan's question is answer is that traditionally I'll start reading from start, and with each occurrence of new word, create a bin, okay, create a hash, and then each occurrence of the word goes into the respective bins. Good, good. This is procedural and linear approach. Yeah. So Amar's point is that using mapper class, don't worry about the mapper. We'll just talking about the basics, and we'll come back to the mapper again. Okay, that is the end result. Now, yes. So, okay. So, Makan, the way you're suggesting that create bins means hash table, right? You create a hash table, you keep on putting words into a hash table, marking the frequencies, right? Histogram sort, right? Okay. Prashant? And others, what is, I mean, did you think about how do you solve this kind of simple problems? These are simple problems. These are generally solved using your traditional databases very, very easily. Okay. Hmm. I understand that part, yeah. Anybody else? So just whatever approach will you take, just write down that approach. It's okay. Even if it's absolutely wrong, but you should, put down any approach. You got huge text file, and all you want to do is find the frequencies of the character. How many frequency of the words? How many times a particular word has come? Just feel free to answer that, and we'll log in onto the cluster later on. All right. Now, I mean, we'll focus on these problems right away. An improvement would be using threading after splitting the huge text file using histogram sort, and then merge the results from all threads. Good, good. Now, problem with uh, all of this is, so my question to you, Virdi, is that these bins or words, are they stored in memory or on the disk? Memory, right? So 10 GB, for 10 GB words, you will have the upper limit is at least 10 GB, at most 10 GB you would require the RAM in case you don't have the 10 GB RAM, or in case you have 1 terabyte of data which cannot fit in the RAM. Right. So in worst case scenario, and remember that whenever we are forming a hash table or any kind of bin, on an average it's 4x memory which goes, which means 40 GB memory you would require. The Python hash table is 4x. So my question is that how would you handle how would you handle such a scenario? Writing a scratch file might help. Okay, okay. This is interesting. So, but again, how would you write the scratch file? That's the point. Again, you'll have to look up into the scratch file every time a new word is coming, right? Need to split the input data. That's Amar's point. Okay, okay. Prashant, are you guys back? Uh, Bhupati? Okay, okay. Okay, so I'll just be a little louder in case others don't feel, you know, I'm shouting. Great. So Prashant, my question to you was that you said that first sort and then count. That's a good answer, but how do you sort a 10 GB file? Okay, write 26 scratch file on the disk, one for each alphabet A to Z. Okay, and every time you encounter a word, you look up into that uh, bin, right? That's what you are saying, Virdi? Okay. So every time you encounter a word, you will be reading the disk. You will be reading the disk to read this data, right? And the disk read is extremely slow. So if you have a billion words, or not billion words, more than that. Right, right. But it's not a great workaround if you see. If you got a billion words, if you will have to read the data billion times. Okay. So you split the file into manageable size as much as you can give memory limitation, and then good. Then sort it and count the word. That's a good point. Okay. Okay. Or there are multiple ways. Say, for example, you first pick up, you go through this file, say 26 times, and read only the words which start with A in the first pass. Then second pass, you only read the words which are starting with B, and so on. You keep on doing it until you finish with all the words, right? So there could be multiple approaches, and then you can sort each of these: A first, B first, then C first, and on so on. There could be multiple approaches. I was looking forward to multiple approaches from you guys. Well, good, good. Now, so first approach, which we talked about, creating a frequency table for each word in the file, and then as soon as for sorry. So first of all, you create a frequency table. For each word in the file, increase its frequency in the hash table. When no more words left in the file, just print the hash table. This is the first approach which we do. The only problem which we face with this kind of approach is that you cannot go beyond the data. You cannot process the data beyond the RAM, right? Now, second approach is, I mean, if you are really solving this problem in real life, right? If I am in your position and I have to solve this problem, all I would do is I will somehow push this data into my relational database and then use my uh, technique like select word count star from a table, right? That should will give me a good response as well, right? The only problem with this is and the second problem. So this one basically most of the databases handle this kind of scenarios very well. Okay, and we'll give you the results quickly. Now, third approach is this one. This is interesting approach. So on a Unix command line, replace the space with a new line, right? When you do that, what will happen is that each line will convert into a single word, only word in a single line because you have replaced the space with a new line. Now order these lines, sort this data by using sort command, and then and here I have used sort minus s 1g. Okay, so the sort command luckily provides us this option of restricting memory to a particular size. Here I am restricting the memory to 1 GB, sort minus s 1 GB, right? And then that's it, you're done. Okay, and once you are sorted, you can say simply unique minus c, and that's all. And this works well. This works well for a decent amount of data. So do you guys see any problem with this? These two problems, the approaches, like one is using MS SQL or MySQL or any other relational database, and second is using Unix. In Unix, it solves the problem of the RAM, right, Prashant? The way you have explained. So that's how it does it using the sort command. All right, that's how it does it using in the sort command minus s. Internally it splits the data into whatever size you specify into those size of chunks and then merges it, right? So do you see any problem with these two approaches we talked about in second and third? Anybody? Second approach was to use SQL. You dump all of your data word by word into SQL and then you do the count. Second was using the Unix command speed, right? Good, good. Speed. Why would that be, and how? Okay, okay. Anybody else? That's interesting. Good. So what is the problem with these two approaches? One is SQL one and this Unix command. What are the problem with this approach? Yes, it is basically linear and the speed is going to be a problem. It basically works around the memory bottleneck, right? So Anybody else? Data is not structured in RDBMS and requires a schema. Yes, so data you will have to split and make it single column, and that would require a little bit of effort. You're right, Amar. But that's not the main problem, because once you are done with the converting this file into one word per line, then your problem is solved. But your problem of non-structure is solved. So what do you think would the problem be? And that will be a huge database, since all words will occupy the same amount of memory. Yes. Yes, more data will not be managed in RDMS. That's a good point. Okay. Okay. Yeah. As you go beyond, keep on growing the data, you cannot manage that using your traditional RDMS. Okay. So here are few problems. So if you guys remember, we talked about four aspects: RAM, network speed, and network, and disk and CPU, right? So the moment we started hitting the RAM, the RAM became insufficient. What we did was we shifted the load of RAM to the disk by splitting the file and doing all sorts of magic, right? Now, after some time, when you put it on the disk read write will become a big issue, because it's the same disk which is being read again and again, and you will be able to churn the data only at the speed of the disk, right? Only at the speed at which we can read the data from the disk. Also, after some time, if you have added multiple disks and put your data onto multiple disks, and you can read all of these disks parallelly, right? You have say 100 small SSDs available onto local machine, and you have distributed your file onto these 100 solid state drives. So now you have enough of hard disks, right? From a read and write speed, and you're parallelly reading from all of these and writing to all of these. Now your CPU will become bottleneck after some time. And the only way to overcome such kind of problem is using multiple computers. Okay? Now, these three problems did not work out well for a huge data. Huge data. So what do we do? What do we do? We use an external sort. Okay. We split the files to a size that fits the RAM and use the previous approach, the second and third, to find frequencies. Okay. So what I'm suggesting to you is that we split the file to a size that fits into RAM and use, yeah, it's the same approach which we discussed earlier, that we have split it to the data, and then to multiple machines. Okay, so here we are talking about external sort. Okay, so how does external sort works? So there are two machines provided to you, machine 1, machine 2. What you have done is you have taken your file and divided the file into two portions, file 1 and file 2. And say file 1 sent to first machine, second one sent to the second machine, and let these machines sort the data and give you back the results. And once the data is sorted by both of them, you can merge them very quickly. It is quite easy to merge the data which is already sorted, okay, and it still stay sorted. And even the commands like sort minus m in Unix basically merge the sorted input, and it's extremely fast. Okay, so this external sort is clear to you, right? So let's take a case of you. We are sending to machine 1 sa comma ray, and ga ray is being sent to machine 2. Machine 1 replied back saying ray is 2 and sa is once. And similarly, machine 2 said that ga is twice and ray is once. And both of these are sorted if you notice. G is coming before R and RE is coming before SA. So, and then merging these two inputs on the single machine would take very small time. Very, very, very small time. All right. Does it make sense to you? Was I able to explain to you here? So we splitted our file, sent to two machines, and each machine did the counting for itself. Okay, the way we were talking about approaches earlier, in this is in the approach second and third or maybe first, let each machine sort this data and be happy about sorting, and then, or maybe you have already created two files containing these two chunks and stored on these two machines, and let these two machines sort it for you, and then you merge the data. Okay, and while merging, you can also do the summation of counts if required. The way we have done summation of count here, ray came 2 and ray came 1 from these two different machines, and then we counted it as ray is thrice. Does it make sense? Is it, I mean, did I not make it clear, or just feel free because I would love to explain it again. This is a very crucial point. So Prasant is okay, Virdi is okay, Sini is okay. Rajnikant is got it. Okay. Just feel free to, if you want me to repeat, I'll like to repeat it. Okay. Because these are very crucial points to understand. Okay. Amar is okay with it. Or do you mean to say, Amar, that should I repeat it? Okay. Okay. Cool. So we had a huge file, right? And we want to sort it. We want to count the frequencies of the words. So what we do is we split this file into two portions. One portion we send to one machine, other portion we send to other machine. Let each of this machine do the counting for you. Okay? And once it returns the counts, those counts need to be in an ascending order or descending order, whatever format you want, and then you merge these two. So if you see here, we sent sare ray here to machine 1, it returned the counts, and similarly we sent ga ga ray to the second machine, and then it returned the counts. I've taken very simple example just to give you an idea what's going on. Okay, here the chunks are like 1 GB both. It could be huge also, and let both of them sort it and give it to back to you, and then merge it. Merging is quite straightforward. When you have to merge the sorted data, it is actually quite straightforward. Okay, you can visualize the whole merging thing. If you have to say there are two queues of people who are already standing in an increasing order of their heights, if you have to merge these two queues into single one such that they still remain, the line which you are forming again, the queue you are forming again is basically again in the increasing order of the heights of the people, then it's quite simple, right? So you stand in front of the two queues, and whosoever is shorter, you take him first in the queue, and then put into the fresh queue, and then keep on doing it again and again until either of the queue is finished, right? This is how you will do in the real life, right? So merging the two sorted outputs is quite easy, and then and that's so that can be done on a single machine very quickly. All right. The only downside is that there is a data transfer happening that you cannot avoid right away. And Further to this diagram, there could be hundreds of such machines operating, and this data which you're giving to each machine could be in GBs, and hence this is how you use this technique, right? Now, if you start writing this kind of thing, the problem with this approach, what problem do you see with this approach? The only problem with this approach is that we have to transport the data all the time, right? We have to send this data and let them process. What if we could store the data in the say already in a uh, well-defined format? I mean, already distributed format. Okay. What if the file already existed on first machine? What if the file existed on the second machine already? Right? That could have been like wonderful. The chunks had been already available there. We don't have to split and we don't have to transfer. We could have saved the life, right? So those are the problems with this approach. Second, it requires a lot of engineering. Every time somebody asks you a problem, you will be planning to divide the data and merge the data and do all sorts of magic all the time. And each simple problem such as give me the average amount which customers have been billed for, would take few programmers to again code it all, right? And that is the problem with this approach. Do you see any other problem with this approach? Yeah. Otherwise, this solves our problem. This approach solves our problem. It is just that first, this file need to be transferred again and again. If we could just take the benefit of something like a HDFS structure where you already have 64 MB of chunk available on all machines, then all machines will be busy doing your stuff and then you can churn your data quickly, right? So these are the yes, you are right, Virdi. Virdi's point is that we will still need to transfer the answers or answers data to one machine to merge it and then give the file. Yes, that is something you can't avoid right now. All right. So, but the major chunk generally, what happens is that the results which you are expecting from all of this processing are far more smaller. Even in this case, the results will be smaller because multiple words will be, marked as duplicate, right? So there are high chances that the result will be less than one tenth of the total size. If you think about dictionary, If you think about dictionary, the counts will be equal to the size of a dictionary, no matter how big a English text it is, right? So mostly in almost all problems, when you do the churning, when you do a lot of summarization, aggregation, then the actual results are actually smaller, right? Now, Now, for these reasons, we require a map reduce paradigm. We talked about four problems. First was simple one, we're maintaining the hash table and do the counting. Second one, to overcome the memory restrictions, we came up with something like a Unix approach, where we split the file and then do it. And then we stuck with the uh, problem with the disk speeds or CPU speeds. Then finally what we did was we distributed the logic to the network. Now our network became an issue, right? Network became an issue as in we were transferring too much data here and there. Now, now to overcome the network, the fourth problem which we discussed was to start thinking in terms of map reduce. We have already distributed the data. Can't we take the benefit of that distribution, right? Our half job is already done. Transferring the data to the node is already done. We don't need to do any further. And that's where the map reduce comes in. All right. Okay. So Vidhi's point is very good. He says that in Hadoop, who does the merging of all the responses from client data node? Okay. It can be any of the data nodes. Okay. It can be any of the data nodes, or it could be multiple data nodes. We'll discuss in detail how can more than two data nodes merge the data. Here we saw that only one node merged the data. Okay, because one node has collected or gathered the data. We can have multiple data nodes. All right. Good, good. Now that's where, so as we told earlier, we had few memory restrictions. We had CPU, RAM, disk. Sorry, we have four bottlenecks. We defined four bottlenecks: CPU, RAM, disk, and our network, right? And these problems made it clear that though either of those four bottlenecks became our problem when we tried to solve a simple word count problem. We tried to solve a simple word count problem, and and all four poses various kinds of restrictions. All four, I mean CPU, RAM, hard disk, and network, all four became bottlenecks at one point or the another. All right. To to make optimum usage of all of this, the map reduce paradigm was coined, and this is quite interesting to understand this part. That basically under the hood, map reduce is nothing but a sorting. It is nothing but sorting the data, right? So what is map reduce? It's a paradigm which helps us solving big data problems, specifically the problems which are sorting intensive. And for doing map reduce, you'll have to write two functions. One is for mapper and other is reducer, right? Mapper converts every input. Mapper, which is your code, its duty of your code is to convert every line into key value pairs, and reducer simply aggregates all the values for a key. Okay, we'll in the next screen we'll go again and again into details. And this is map reduce is not only a specific to it's not only specific to our Hadoop. There are multiple systems starting with MongoDB, CouchDB, Cassandra. Everybody has started supporting MapReduce paradigm. And MapReduce can be written in Java, Shell, Python, or any program or any library. We can write a MapReduce code. All right. We'll show you. In Java is the standard way. Shell, Python, or any binary is the called streaming way. Okay. Now moving ahead. So mapper basically is right. Let's talk about this. This will make it clear to you. Now we will just take the word frequency problem again. Okay. So we have got a huge corpus of text. Huge in the sense like here we are only talking about four words: sa, re, sa, ga. Okay. It's a just for time being so that I could fit in into the diagram. I've taken only four words. In practice, there will be billions of words. Okay. So we have to find the frequencies of our word in this one. How what kind of map are we going to write and what is it going to be reduced? So in the map is your function, okay? Map is your function where you are writing the code, okay? You defined that go through each word in the input line, okay? And print line by line. In each line, print word followed by 1. This is 1, not L. This is 1 as in numeral 1. So at the end of it, and at the end of this process, it did nothing. It only converted it into key value pairs. It converted each word into key value pairs. Sa1, Re1, again Sa1, and Ga1. Okay. It only converted this whole line into word per line, and against each word we just printed 1 as a numeral. All right. Now Hadoop will take this output of your map. Hadoop or MapReduce, the underlying framework, is going to take this output, and what it is going to do with this output of your map, it is going to sort it. Okay, it is going to sort it, and after sorting, it is going to combine same keys together, right? So what did was, first it sorted, which means ga came at the top, and the frequency of ga is only 1. Okay, ray came as 1, just like ga. And then sa has got two values. Sa is a key, and guy is also Sa is also, I mean, all of these are key value pairs. So Sa has got two values, 1 and 1. So MapReduce converted your output into something like a group by the key. Okay, Hadoop took your output of the map function and grouped it by the key, and it is sorted. So Rajnikant's question is interesting. MapReduce is only used with text input, or can I give a table? So any database, so his question is that, is it only good for MapReduce, or you can, yes, you can actually use it with database table also, but you would require a specialized library to read row by row. Okay, the way we are reading line by line from plain text, we can also read in the same fashion, row by row. And there is a different, slightly different version of MapReduce available for churning HBase. HBase is a database. Right. Now, so the Hadoop only did was, it took keys and grouped all the values for that key. And here, what you did was, you cleverly converted your input, converted into your input file into key value pairs. And the value you kept as hard coded 1 right now for this example. You could keep any values, or you could keep hundreds of values for each, hundreds of keys, hundreds of key value pairs corresponding to your single input. It is up to you absolutely. Okay, how do you want to solve your problem? Now, so Hadoop did a good thing for you. Hadoop did a grouping for you, group by key. Basically, it's like sort the data group by key. That's all Hadoop did. Now, your reduce function will take these grouped values and flatten them out in whatever format you want. You want an average, you want summation, you want this, you want that. You can do all of this using in your reduce function. Does it make sense to you? And this map, now, this is good. This is simple. That there was a single file we loaded using map. It converted into key value pairs. And then Hadoop, your map function converted your input text into key value pairs. Hadoop took your key value pairs, grouped it by key, and then passed it to reduce function. Your reduce function just summed up the values. It could do average. It could do root mean square value. Whatever you want. It is your duty to write this code. It is your duty to write this code. All right. So whatever you want to do with these values, it is up to you absolutely. What if we have binary files instead of text file? That's a good point, Makan. So the thing is that in case of binary file, you will have to write your readers which can read the binary file, and you can do the similar processing. All right. And here you have your frequencies. So to reduce in map, you will be passed, you will get a variable corresponding to each line. Okay, corresponding to each line. And in reduce you will get key and the array of the values. All right, you will have to operate upon that. So is this clear? Is this one clear to you? So here this dashed line is something which is being done by Hadoop for you. Okay, Hadoop will execute the map function, collect all the output of your map function, and that output is now grouped by the keys, sorted and grouped. And sorting is done exactly the way we were trying to do earlier by distributing it across the network. So is it clear to you guys? Vanaja, Amar, Bhupati, Prashant, Rajnikant, Sini, Virdi. Good. Vanaja, you can write to all the people. That's okay. That's okay. Yeah. You don't have to write to me in private because everybody can see the answer. It'll be great. So Virdi's point is good. So he says that ev- so MapReduce logic is executed every time we run our jar program on all the data nodes. Yes. Yes. How does image file get stored? If they get stored, how do we read them when processing? Would it not give error since you don't have a complete file? Good, good. So it is absolutely up to you how do you handle this file. By HDFS will have a hard limit over there, but you can write your own handlers and write those handlers to handle your binary data such that Hadoop does not when Hadoop is reading a chunk, Hadoop is giving the input to your map function, it will give the input as per your demand. We'll come back to this point. This is a very interesting point you have raised in maybe next session. I have a similar example for the same thing. So basically, before giving map, there is a one more phase over here. When before giving the input to the map function, it reads from the disk and then try to find out using your logic whether this data is good enough or do we need to transfer some file or some data from other nodes to this node. All right. And yeah, yes, for different type of data, you will have to write this implementation of map. It is your duty to write the functional implementation of this map as per your wishes. Right. Move on. Good. Now, same thing I have taken and spread it. So here this was fine. It grouped our data and everything. Now, same thing. I'm trying to demonstrate what happens on multiple machines. If you have more than one machine, for different type of data, we need a different implementation of map function. That was the question by Sini. So okay, so what my answer for this was that whatever kind of data you have, whether image, whether binary, whether you are reading from database, okay, you can write two things. One is the data reader, which will form the inputs for your map function. Okay, so data reader's duty will be to form the inputs from the for the map function. And similarly, the map function can have its own implementation in a decent fashion. It can be different for different situations. Okay, the map function can be will be different for every situation, and you will have to write that map function. Okay, in this case, if in case you want, you can put one key per line, and that's exactly your role in the game. Okay, that's exactly your role in the game. Okay. Okay, good. Now, if our target data of interest resides only on one node, will it still run on all the data nodes? Okay, so when I talked about resource manager or task tracker, or sorry, job tracker, resource manager, their main role is figuring out what is the best for you. Okay, whether even if the file is located on a single node, does it make sense to distribute it on multiple nodes, or does it need to be done on the same node? Which one will be efficient? Okay, that it does by sampling your data. Okay, and then it figures out if the data is too huge to be processed on a single machine and it is not split properly, or your MapReduce, when it was run last time, it took a very long time, then it will figure out that this thing, your MapReduce, is quite process I mean CPU intensive, and therefore even if the data is smaller, and your MapReduce will be run across the network. Okay, so even if your file is located on a single machine, which means 128 MB, still there are chances that it will run on multiple one, but by default it runs on single one. I've never seen it running, but in theory, if your that particular node is busy, or ha- in your past, you have been running the same jar again and again, and Hadoop has gathered enough statistics about your process, then it might run on multiple nodes. All right. Now, next question is, will it run MapReduce logic on all the nodes every time? Yes. Yes. Every time. All right. Now, the same thing what I did just now using a single machine. This is the visualization of what goes inside Hadoop when you do this. So node 1 has this data, node 2 has this data, node 1's map converted. So each with respect to each stage, you have these outputs. So as a result of first, you have sa re saga. Here it's sa re sa, right? And map converted that into key value pairs. Sa 1, re 1, sa 1, ga 1, right? This is a standard word count problem. Here similarly at the two second stage, this is the output. Now here sorting happened, and this data is sorted, and then the merge and shuffling is happening. So the grouping will happen, and then splitting will happen again. So this is the case where there are multiple reduces. Okay, this is the case where there are multiple reduces. Generally generally there are only single reduce function. Okay, generally there are single reduce function, but here, just for demonstrating the flow of the data, I have put it here. So as a result of 4, what will happen before 4 is all of this data from both sides will be combined and then split. This shuffling will happen in order to carry the keys from one machine to another one. Those keys which belong to another one. So say you have A to Z data. Half of the data will go to one reducer and half of data will go to another one. And basis would be based on certain definition. You have to give the definition on what basis I need, on what basis I want my reduce function to be executed onto multiple machine. All right. Yeah, otherwise it will just does some sort of sampling and will divide your keys. Okay, for time being you can just think of it as a single reduce, so your data gets merged and shuffled and then you have the results. That's all. But the name node knows where the data is stored, right? Yes, name node knows. Right, so that's what I was saying, Rajnikant. So in case it has a history of your MapReduce job, and your MapReduce job are known for taking long time and too much of processing, there are chances that Hadoop will distribute your job even if the data is not there on another machine, and it will transfer some of the data. Okay, and this mechanism keep on improving from one version to another one. Okay, every version have a little bit of differences with respect to this particular aspect. Yes, Hadoop keeps track of your resources and keeps track of your processes also. It keeps on just like the debugger keeps on making a note of how many times a function is called. In the similar fashion, keeps on recording it. All right. So is this clear? Is this not clear to anybody? So if it's not clear, just let me know. Maybe I've not simplified enough. All right, so let me just think of this as a single reduce. And here on the second stage, now after this stage, you only have one, okay, like this. All right. Step four, okay. So here what I'm trying to demonstrate that this is a single reduce, okay. This is a single reduce. We'll talk about multiple reduce. So here, so after third step, the data from both the sides have merged into single one, right, and brought together, and then after the reduce function is run on it, you see the re which has come together, which will give this output. Okay. Okay, or here how you can visualize it simply is by putting like this. All right. Right, right. So multiple reduce is an interesting phenomena in which a shuffling happens in the sense that it figures out that which ranges it need to keep on one machine of the keys, and in which ranges need to be kept on another one, and then take some, because the data is ordered anyway on both the machines, right? So it can quickly take some of the keys from one machine and shift it on another one, and that's what we call a shuffling step. Yes. So sa, as you see, the sa is not here on, sa is not on two machines as a result, if you see. Okay, and that's exactly what it is. So sa was transferred, sorry, ray was transferred from this side, left hand side, to right hand side. Okay, here there is a single reduce phase, this is a multiple reduce phase. Here ray was transferred from left hand side to right hand side. Okay. Sorry, ray was transferred from right hand side to left hand side to ensure, okay, here like this, that will look better, right? So ray was transferred from left hand side, right hand side to left hand side, and sa was transferred from left hand side to right hand side, right? So that same keys will always be on the same machine, right? Good, good. So this is clear, right? So basically in the reduce, all the keys have to be at the same machine, right? Now, so for multiple node reduce, when it is deciding where to send which group, it can merge in the same amount of effort, I think. Yes, yes. So even that shuffling does is little intensive, but we'll come back to that again. You have a valid point. Basically, there is a way to define your own reduce, own splitter also, that this key should go on to first reducer, this key should go to the second reducer, and so on. Based on number of reducers you define, you can tell, given a key, send it to this particular reducer. Okay, reducer is a numeric value that ith reducer you send it to. Okay, you can do that also. Okay, okay, that's all. So I'm moving on. The other way to look at MapReduce is that MapReduce is more like analogous to your group by clause. The way we have select word comma count star from table group by word. So table is our data source over here, from the where our we are reading the data. So these two things, which is colored one, grouping by word and then select word, both the things are being done by map, while reduce is being done in the is equivalent to the aggregation function. Okay. So as a result of map, you did not do any sorting or anything. All you did was told Hadoop that this is my key, and Hadoop sorted your values with the key and combined all the values for a key. Okay. So sorted your keys, not sorted the values, sorted the keys and combined all the values for a key. Okay, that's all it did. Now I'm leaving you with this assignment for today. And these are 4 questions which I want to leave you with. And then we'll discuss it tomorrow. All right. So this is clear. The whole map reduce paradigm is clear to you, right? Sini? Okay. Okay. Good, good. So Amar, Sini, Prashant, Virdi, Vanaja, good. Pupati, good, good. So we all have understood like how does MapReduce function. So basically in MapReduce we write some code which convert our input into key value pairs. Hadoop takes that output, sorts it, and groups all the values together for a key and gives these values this with the aggregated values for each key to your reduce function. Reduce function can do anything with the values, whether summing it up, doing root mean square value, anything. Now, my question to you is, first question is, same question, same text file, 100, what that file? It was some 10 GB file, right? So same 10 GB file, I want to just compute the frequency of letters and imagine it all, and we just want to ignore if there is numerals or apostrophes, all those extra characters. We just want to ignore all of those. All I want to do is want to count the frequencies of letter A to Z. That's all. No numerals, no special characters, no punctuations, nothing. I don't want to count anything. I only want to count the frequencies of these 26 things, 26 letters, right? So do I still need MapReduce? Does it still make sense to use MapReduce for doing the same thing? It would be easy, right? If I have to do map reduce for this, all I will do is we'll create key value pairs, right? We'll create key value pairs. Key is by letter and value is 1, and let it aggregate. So does it still make sense to do that? Anyone? Okay, okay. Since these are only 26 letters, we can only keep these in the memory, and we can, just pass through the whole file from left top to right bottom, and then only keep on counting these 26 letters, right? Okay. But it might be far. Yes. Okay. Okay. Think about it. Think about it. Right. Think about it. Yeah. Virdhi has a point. All right. Now the next step is to give in a huge text, huge input text. Okay. Just think about it. I mean, does it still make sense to do all of this? Okay. Virdhi has a point. Yeah. Thank you, Virdhi. Okay. So now the second question is find anagram in a huge text. Okay. An anagram is basically a different arrangement of letters in a word. Okay. We have got the cat act in tic-tac-toe. Okay. The output should be this one. These are the anagrams of each other. If we have to find anagrams, what will you do? And see, there is a huge file. There is a huge file, and what all we want to do is, anagram is basically different arrangement of the letters. For example, there is no anagram for the. Okay, if had it been EHT or some other and HET, then they could have been anagram for the. Okay, so okay, to make your life simple. Okay, and the two in, that's all. So this output is also okay for me. Okay, which means the characters which are anagrams to each other should come together, while the other one don't have an anagram, so there are only single in a line. And you have to write this. You have to do this using MapReduce, always thinking that this data is huge. This data is 10 GB. What will you do? Okay. So question here is solve this problem using MapReduce. The second problem is strictly for MapReduce. There are multiple ways to solve it without MapReduce, but this one is specifically for MapReduce. Okay. Okay, with this point is that we will first get the words with the same length, and then within words we'll look for the distribution of individual words, individual letters. Okay. Okay. So you will in your map function you will get line by line of each of these words, and then you will have to form the key value pairs such that all the anagrams come together. Okay. This question is clear to all, right? Think about these questions before we meet tomorrow morning after 24 hours. All right. We'll discuss these questions in detail again. All right. So this sounds good to you? Okay. So try to think about this question in terms of MapReduce. Now next one. Next one is little difficult. So you have got a huge DNA sequence of the people of the whole world, and you have got a file in the form of username, then followed by a tab, and then DNA sequence. Okay. DNA sequence is generally of ACGT characters, right? Now, your duty is to find all the people in this world who have the same DNA. Simple, right? Using making the proper key value pairs, you can solve this, right? Just think about this problem. So how do you find all the people with exactly same DNA? Question is clear, right? Is question clear? You are given a big user followed by their DNA in a file, and you have to find out the people with the same DNA. It is same as word count problem, just little twisted one. Okay. We have to find out, you have to bring together the people with the same DNA. Okay. Now the next step, a particular research showed you that people with identical DNA or people with exact mirror image of the DNA are the people who belong to the same family. Okay. Okay. So a particular research says showed you that the people with the exactly same DNA or exactly mirror image of DNA belong to same family. Now your duty is to bring these people together, bring the families together who have either exactly same DNA or identical reverse DNA. For example, here you have user 1 and user 2. User 2 is exactly opposite of user 1. It is ACGT and this is TGCA, and user 4 is ACGT. So user 1, 2 and 4 belong to the same family, while user 3 and 5 belong to the same family. Okay. You have to solve this also. Okay. How would you do it? Using MapReduce. Okay. So that's a deviation from third B. Now fourth problem is little further difficult. Okay. The fourth problem is that imagine, and you will be surprised that this is exactly the reason whole MapReduce was coined in first place. Okay. It's similar to PageRank from Google, but this is simplified PageRank. Okay. Now it's an unusual democracy. Unlike democracy of India or any other country, it's an unusual democracy. Here, the vote of rich person is bigger than the vote of the poor person. Okay, so you are given two big lists of two big files. First one contains people who voted for who. Okay, who voted for who, and second one contains what is the worth of each of the person in this strange country. Okay. Now your duty is to, given these two lists, you have to tell how much each person got the vote in the end, and how much each got the vote is based on the summation of the wealth of all the people who voted for a person. Okay, the people who voted for me, if you sum up all their wealth, then that is the in that is the basically my vote count. Instead of doing count, there five people voted for me, I got five votes. Instead of that, My vote count is the summation of wealth of these 5 people. All right. Now, how would you solve this kind of problem using MapReduce? Same paradigm, where given a line, you convert it into key value pairs and let the Hadoop group the values together, and then you write reducer function which does this for you. All right. Is this problem clear? This one and the DNA one. If it is not clear, I can repeat. And remember, both these lists are hues. In this democracy, people vote for each other. Okay, there are not only few 50 people to which you are voting. So, Amar, which one is not clear? Fourth one? Fourth problem is not clear? Yeah, okay. So, basically, in this democracy, you have two lists. One is voter and votee. Here, A has voted to C, B has voted to C has voted to F. Okay. Now we are also given a wealth of all the people. Like wealth of A is 5, wealth of B is 1, wealth of C is 11. Okay. Now for C, he got a vote from A, right? Now, so C has got vote from A and B, and the wealth of A is 5, wealth of B is 1, right? If you sum them up, it is 6, right? So the vote count of person C is 6. Similarly, F has got vote from C, and the C's value is 11, and therefore the wealth of F is 11. All right? And A, nobody has voted for A and B, therefore their vote count is 0. Yes, yes. Great. Thank you, Virdi. All right. So does it make, is it clear to you guys? Prashant and Vanaja, Amar, Bhupati, Prashant, Rajnikant, Sini, Virdi. Excellent. Excellent. So tomorrow. Let's meet tomorrow and think about how can we write MapReduce for these things. Okay. And remember that you do not have to write code for it. You do not have to write, if you are able to, write a simple steps that my map will spit out this key and this value. My reduce will convert these values into this value. That will be good enough. Take a decent amount of input sample size and then uh, sh- depict that out of the step this is what my output is. That's all. What is the key you choose, what is the value you choose, it is completely up to you. And what does your reduce function does, that also is up to you clearly. Okay. So you don't have to write code, you just have to think in terms of key value pairs. And remember, I mean, thinking in terms of what does Hadoop do in when we are given key value pairs. It basically sorts the data, groups them by key, and then applies the aggregation function. It is as simple as that. Okay. And also remember, when you are solving these problems, that you can apply MapReduce passes multiple times. To MapReduce in sequence does not make any sense. But if you think in terms of map, the output goes to Hadoop, and then the output goes to reduce, then the output goes to HDFS where the file is saved. Again, another map 2 you can say, will be executed again. And so this is the way you can keep on working with multiple Hadoop sequences. Okay. So when you're thinking about these problems, think that you can have multiple passes of MapReduce combinations. Okay, and also remember that reduce is not always required. If you don't have a reduce, it's also okay. Your output will be basically groups of things. Okay. All right, guys. So I take a break today from here, and tomorrow we'll go deep dive into further steps, the concerns which have been raised by in team, like what we do in case the binary file is there, what we do in case there are multiple reduces we require, how will the shuffling happen. Those kind of things we'll go into a bit of detail and then see how it happens. And also we'll do a okay, right? So let's do that. Okay. So we meet tomorrow again at the same time, and we try to solve these problems. All right. Thank you very much. And it was a pretty interesting session. And keep interacting. Think about all the problems, write them down, drop me an email, and then or discuss tomorrow tomorrow morning in the session. The biggest use of these sessions is that we can discuss the problem, we can try to answer all the problems. Okay, otherwise there are hundreds of websites where you can watch a video and no. So the biggest role of these classes is that you should ask the questions. All right. All right, thank you very much, have a good day. And for those, have a good night who are in US. Bye bye. Looking for the tomorrow session. And good night, Vidhi. Good night, Prashant. And so Vanaja, these okay. So all these problems are available. All these problems are available, will be available in the session 2 page. I'll have to enable those. Okay. On the course page, there is a second session. Here, those problems will be available in a few minutes. Okay. And these PPT and recordings, they are all going to be available over here. All right. They're all going to be available over here. All right. Thank you very much. Bye bye.